Right, here we're jumping forward a few sections to the end of chapter 11, talking about the areas and volumes of solids when they are similar to one another. So we'll end up going back and talking about the rest of chapter 7 or chapter 11 after this video, but this is actually the next thing we're going to cover. So I'm going to start off with a question. Newborns are an average of 20 inches and 7 pounds when they are born. How heavy would you expect someone to be when they are 60 inches tall? So I'm sure you all have an idea of how heavy somebody would be that's around 5 feet tall. Obviously, it depends on the person. But I want you to think about this because here, newborn 20 inches, 5 foot tall, 60 inches, their height has been multiplied by 3. But I'm guessing the number you came up with here did not involve multiplying by 7 by 3, right? If you multiply 7 by 3, you get 21 pounds for somebody that's 5 feet tall, and everybody knows that that's wrong, right? It's impossible for somebody that's 5 feet tall to be 21 pounds. So something's going on here, right? That here the height gets multiplied by 3, but your weight definitely does not get multiplied by 3. And that's something that we're going to be exploring in this section because your weight is related to your volume, how much space you take up. And it turns out that when you grow, when your length increases by a certain amount, the volume increases at a different rate. So we're going to talk about that. So first off, what is volume? Volume is just a measure of the amount of space that an object takes up. So in this case, we're going to be talking about geometric figures, but everything has a volume. You have a volume, you take up space, the desk you're sitting at has a volume, the room has a volume, it has an area that you could fill up with something like water or something like that. And that's how we measure volume. And then surface area is the sum of the areas of the solid. So in this case, we would add up the area of this side plus 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 the sides we can't see that would be on the back of the shape. So it's how much area that thing composes on all the sides of the figure. So let's look at an example. What's the surface area and volume of the cube? We're going to talk about how to find surface area and volume of all these different types of shapes, but for cubes, it's pretty simple. We just want to think about how big each side is. Well, it's a cube, so every side is a square. And since the dimensions are 2 by 2 by 2, well, each little square on the side of the cube is going to be 4 feet squared, right? 2 times 2. So we got 4 there, 4 there, 4 there. There's 6 of them, and we end up getting 24 feet squared. And for the volume, it turns out we end up just multiplying all of these numbers together, 2 times 2 times 2. And again, we'll get into that when we go back to the rest of chapter 11, but that gives us a volume of 8. Looking over here at this cube, we again have 6 different squares, the different faces of this cube. And so each of those has an area of 16, right? 4 times 4 is 16. So we've got 16 there, 16, 16. We add all those 16s together, we get 96. And for the volume, again, we're just going to do these numbers multiplied together, 4 times 4 times 4. And that gives us 64. So let's see what happened here. Well, first off, what's our scale factor? Our scale factor is just 2. All of the sides got multiplied by 2. 2 times 2 gave us 4 for all of these. So our scale factor is 2. What did our surface area get multiplied? Well, it didn't get multiplied by 2. Hopefully you can see that 24 times 4 would give us 96. And then for our volume, it didn't get multiplied by 2, and it also didn't get multiplied by 4. It actually got multiplied by 8, because 8 times 8 is 64. So when the dimensions of the cube doubled, the surface area was multiplied by 4, and the volume was multiplied by 8. So you might remember back from chapter 10, we talked about the area already, right? This area is just the scale factor squared. So our scale factor was 2. We squared that, and we got 4. And it turns out to get the ratio of the volumes, we multiply by the scale factor cubed. So we do 2 to the 3rd power, and that gives us 8. So let's put this in general. If the scale factor of 2 similar solids is A over B, then the ratio of their areas is A squared over B squared. We already knew that. But for the volumes, it's A cubed over B cubed. So we cube the scale factor. So let's see some examples where we need to use this. We got 2 similar solids with a scale factor of 3 over 2. We know the surface area of the smaller solid is 50 meters squared, and the volume of that solid is 120 meters squared. Let's find the surface area and volume of the larger solid. So the first thing we need to think about, if we're going to find the surface area of the larger solid, is what's the ratio of the areas? Well, we just do the scale factor squared. We get 9/4. And then we need to use that, multiply it times 50 to get our surface area. So our answer here is 112.5 meters squared. Okay, what about the volume? Well, to find the ratio of the volume, we need to do our scale factor cubed. So we do 3/2 to the third power. Each of those numbers to the third are 27 and 8. So that's our ratio of the volumes. We're going to multiply that by our 120 and get an answer for our volume of 405 meters cubed. Notice our units on volume is a cubic unit because it's three-dimensional. And again, we'll talk more about that when we go back to the rest of chapter 11, but our areas are still squared and our volumes are cubed. And notice that that same pattern holds true when we talk about what we do to the scale factor. Here we square it, here we cube it. All right, let's look at a different example. Here we got two similar solids, and we got their surface areas. Let's just find the scale factor. So our ratio of the surface areas is 64/196. And that actually simplifies down to 16/49. We can divide the top and the bottom by 4. So we simplify that fraction. But that's not our scale factor. That's just our ratio of surface areas. But our ratio of surface areas is the scale factor squared. So to find the scale factor, we need to take the square root of 16/49. Square root of 16 is 4. The square root of 49 is 7. So our answer is 4/7 for the scale factor. All right, let's do another one. This time we were given volumes and we want to find the scale factor. So again, let's find our ratio of volumes. We write it out, 32 pi over 500 pi. Those pi's cancel out, and that 32/500 can simplify down to 8/125. And we divide the top and the bottom by 4. But here, this is our ratio of volumes, which is the scale factor cubed. So this time we need to do the cubed root of 8/125. So if you're not familiar with cubed roots, that's saying what number to the third power gives us the thing that's in the root. In this case, what number to the third power gives us 8? 2 does. What number to the third power gives us 125? 5 does. So our answer is 2/5. Now, if you're not familiar with this, your calculator can do it for you. It's a little different than doing the regular square root. So if you can't figure out how to do this on your calculator, let me know and I'll show you. All right, one more question. We got two similar solids. The smaller of the two solids has a surface area of 22 inches squared and a volume of 10 inches cubed. And the larger solid has a surface area of 198 inches squared. We're going to find the volume of the larger solid. Okay, so we know the surface area of both. So let's find the ratio of the surface areas. Divide those values and we get 9. All right, let's use that to find the scale factor. To go from our ratio of surface areas to the scale factor, we just need to take a square root. So our scale factor is 3. Next, we need to think about what is our ratio of volumes. To find that, we would need to do this scale factor to what power? The third. That gives us 27. And finally, we're going to use that 27, multiply it times our volume of the smaller solid to get our answer of 270 inches cubed.